Now we're going to look at section 5.2, which is on infinite series, which before we looked at sequences, lists of numbers. Now we're going to start adding them together. Series means an infinite sum. And the notation, the sigma notation, is a capital sigma with, like the bounds of integration, the index ranges from 1 to infinity. So n equals 1, n equals 2, n equals 3, n equals 4, and so on. We're adding up not the numbers n, but the terms of a sequence an. So the sequence itself, I'm just going to list it here and then put it together. So the sequence is a1 and then a2 and then a3 and a4. But the sum is equal to what I get from adding all of these together. And then more. So the ellipsis, the dot, dot, dot means to continue in this pattern. That's really what we're going to study. What are the patterns that we can find in these kinds of lists when we add them? So to do this, we're going to use something called the partial sum. And the partial sum is, well, we're going to add up the first k terms of the sequence. So instead of adding up all infinitely many terms, we're just going to add the first k, in other words, a1 plus a2 plus a3 plus up to ak, and then stop. So that's just a finite sum that obeys the ordinary properties of addition and rearranging terms or whatever that you're familiar with. It's a finite number of numbers. It might be a large number, but in any case, it's finite. So the notation for these, let's look at some of them. The S1 is the first partial sum, and that's really just the first term of the sequence. So nothing special there, but S2 is the sum of the first two terms of the sequence, the second partial sum. S3 is the third partial sum, which is the sum of the first three terms. And in general, I'm going to write part of this just to emphasize the pattern. A1 plus A2 plus all the way up to AK. That's the kth partial sum. And that's actually really the important character here is the kth partial sum. We're going to use that idea to find a way to define a sum of an infinite sequence. An infinite series is the sum of a sequence, all infinitely many values. And let's look at an example. Oh, let me write that down. The kth partial sum is the idea that we're working with. Kth partial sum, SK, is the notation for it. And we're going to do an example. We're going to look at an example with the sum from n equals 1 to infinity of 1/2 to the nth. So just to emphasize what my terms are, my an, my sequence, is 1/2 to the n. Now the series is the sum of all of those. We can list this out. This is 1/2 to the first, that's 1/2, plus, this thing is equal to this, plus 1/2 to the second is 1/2 squared, or 1/4, plus 1/2 to the third is 1/2 to the third is 1/8 plus 1/16. And you may have seen this before. This sequence is the halving sequence. If I add it up, well, it sums to 1. It's a geometric series, and we're going to see more detail later. But for right now, I just want to approach this as a partial sums situation. And having it written out like this is kind of convenient. We can see the first few terms. 1/2 is the first term just by itself. The first partial sum is just the first term. The second partial sum, the sum of the first two terms, 1/2 plus 1/4, which is, that's 2/4, and 1/4 is 3/4. The third partial sum is 1/2 plus 1/4 plus 1/8. So these terms are getting half as large each time. The denominators are doubling, in other words. But this is 4/8, 2/8, and 1/8. 4, 2, 6, and 1 is 7. So that's 7/8. If I add the first 4, well, S4 is, I'm just going to write it down rather than the whole list. It's so many 16ths. Well, how many? It's 50. And you can do work with the fractions if you want. Let's get to the general pattern though, which is SK. The kth partial sum, following this pattern, not of the fractions before I add them, but when I combine the fractions, 1/2, 3/4, 7/8, 15/16. Notice that the denominator is a power of 2. 2 to the first, 2 squared, 2 cubed, 2 to the fourth. And then that denominator's power of 2, 2 to the first, 2 squared, 2 cubed, 2 to the fourth, matches the index of the sequence of partial sums. So that index, k, is the power of 2 that's in the denominator. Also notice that the numerator is always 1 less than the denominator. So we can do just that number, 2 to the k, minus 1. Not 2 to the k minus 1, but rather 2 to the k minus 1. And that's our general term for the sequence. There's another way that we can write that, which is to say it's 2 to the k over 2 to the k minus 1 over 2 to the k. Well, that's just 1 minus 1 over 2 to the k. And you could write these like this, actually. This is 1 minus 1/2, 1 minus 1/4, 1 minus an 1/8, 1 minus a 16th, and so on. 1 minus 1 over 2 to the k. And if we look at the limit, as k goes to infinity of this sequence of partial sums, this is exactly what we're going to define as the value of this infinite series. The limit of this sequence of partial sums, I'm kind of getting closer and closer to what this is. Well, in the limit, it should be the same. The limit as k goes to infinity of sk, the limit of the partial sums, is, in this case, the limit as k goes to infinity of 1 minus 1 over 2 to the k. I'll write this guy again. just using the final formula for the kth partial sum, not the individual first, second, third, but the kth partial sum. The limit of the kth partial sum is the limit of this expression, which is 1. The limit of 1 is 1, minus the limit as k goes to infinity of 1 over 2 to the k. And this is where we can use our knowledge of sequences to find this value. As k goes to infinity, k gets very large. 2 to the k gets very, very large, but the result is the same. As the denominator grows without bound, the whole expression, because the numerator is fixed, the whole expression goes to denominator grows, numerator stays the same. This whole thing goes to 0. This is 1 minus 0, or 1. And that's what we can describe as the series converges. And the sum from n equals 1 to infinity of 1/2 to the n. That's how we originally looked at it. I like 1 over 2 to the n to describe these terms, but this gives you an easy way to see, well, why this is a geometric series. We'll see that a little bit more detailed later, but that series is equal to 1 because the limit of the partial sums is equal to 1. This is also what it means for the series to converge, because it's not infinity, and also it's not a limit that doesn't exist. It's a limit that does exist and is finite, so that's what it means to converge. I have a graph that might help a little bit to understand what these partial sums are doing. And I'm going to use the same partial sums that we just saw in this sequence. The graph would be kind of like an xy plane, only here I'm going to have the k-axis and it's the y-axis, but I don't need another name for it. The y values are going to be my sk. And the k values range from here's 1, 2, 3, 4, 5, 6. Keeps going. K is out there somewhere. K, just the general variable. The one before it is k minus 1. The one after it is k plus 1. But this is the k-axis. And as I take larger and larger values of k, I'm going to get different values for my sk. Now, I happen to know that these values are all smaller than 1. If you remember, they were 1/2, 3/4, 1/4, 7/8, 15/16. The next one would be 31 32nds, 63 64ths, and so on. That's S1, S2, S3, S4, S5, S6, the sums, the partial sums of the series. The first one, I happen to know that these are getting closer and closer to 1. So for my graph, I'm just going to put 1 on here. And let's think of that as a horizontal line. Now, my first partial sum is just the value 1/2. And then my next one, S2, is 3/4, then 7/8, then 15/16, then 31 32nds, getting very close. And all these are going to do is get closer and closer still as I go on down the line. It's almost like I'm starting with the first term, 1/2, and putting a quarter on top of that, and an eighth on top of that, and a 16th on top of that, and a 32nd on top of that, and I'm just building my way up to 1.